In this lesson, we're going to look at the typical bond angles formed by atoms in each geometry, as well as looking at variations from the norm. Let's first look at linear molecules, and we see that the atoms are 180 degrees from one another. Remember that VSEPR is about electron pair repulsion. So in order for the electrons that are involved in the double bonds of CO2 to get as far apart from one another as possible, they're going to be 180 degrees apart. When we go to trigonal planar, we see that the bond angles are now 120 degrees apart. So this is how the electron groups can be as far apart from one another as possible. And all of those atoms are in the same plane, hence the name trigonal, forming a triangle in a plane. It's a little more challenging when we look at tetrahedral molecules. Remember that Lewis structures show us how atoms are connected to one another. They don't show us the geometry. A common error is for students to look at a Lewis structure of CH4 and think that it has 90-degree angles because of the way it's drawn, but that just shows us the connectivity. When we actually look at tetrahedral molecules, as you can see pictured here, the bond angle is 109.5. Imagine that we had 4 balloons attached together. Those 4 balloons are going to naturally push away from each other because they're occupying space. And the angle that we would see is something comparable to 109.5. So tetrahedral molecules are no longer in a single plane, and they in fact go beyond the 90 degrees that we see in our Lewis structure because it shows connectivity, not geometry. So the ideal bond angle for tetrahedral molecules is 109.5 degrees. We can also look at how lone pairs affect those bond angles. It is not important that you remember the specific values of these bonds in NH3 or H2O. What's important is that you recognize that the presence of a lone pair affects the bond angles. So in an ideal tetrahedral, such as what we see in CH4, we see that we have 109.5 degree angles. In NH3, which has a lone pair, we have 107.8. One way to think about this is to imagine the model of a tetrahedral molecule with balloons. Only one of the balloons is larger than the other 3, and as a result, the other 3 are pushed a little bit closer together. The lone pair has more repulsive powers than the bonding groups, so it will push those other atoms slightly closer to one another. Again, the specific bond angles are not important. What's important is that you recognize that the bond angles are slightly smaller when a lone pair is present on the central atom. Still a tetrahedral geometry, but just slightly altered. When we go to water, which has 2 lone pairs on its central atom, we still have our tetrahedral geometry because we have 4 groups, but now our bond angle is compressed even further to about 104.5 because there are 2 lone pairs which are repelling each other as well as repelling the bonding groups.